In this video, we're going to learn about another test for convergence called the direct comparison test. The direct comparison test has two parts, and this is the first part of it. So basically, what the direct comparison test says is that we've got two series. We have the series AN, and we know that AN converges. And then the other thing that we know is that BN, the second series, is less than AN. So if AN converges and BN is smaller than a converging series, then BN also has to converge. And what that looks like kind of on a graph is that if AN is converging, it's sort of asymptotically approaching something, and then BN is smaller than that, so that means that BN also has to be converging because it can't, for it to diverge, it would have to like shoot off towards infinity or something. But it can't do that if it's smaller than AN because it has to stay underneath AN. And we'll see how to use this test in a couple of slides. So it's important to note at this point that you get to choose what AN is, and the problem will give you BN. So we get to pick a series that we know it converges, and then we compare our problem with the series that we picked. And this is the second part of the direct comparison test. So this time we have a series AN that diverges, and we know that AN is smaller than BN. So this is what it looks like. AN is diverging, so it's shooting off towards infinity, and BN is bigger than a diverging series, so that means that BN also has to diverge. And same as for the first part, you get to choose what AN is, and the problem gives you BN. So before you can even use the direct comparison test, you have to figure out, do you think your series that you're given, do you think it converges because you'll use the first part, or do you think it diverges because then you'll use this second part here? Another important thing is how you choose AN. So remember, they give you the infinite series BN, but you have to pick AN. So here are some examples. The first tip for this is to pick a simple version of the series that they give you. So if your series that they give you is 3 over 5 to the n, then maybe we don't need the 3. We can change it to a 1. 5 to the n we have to keep because it's got an exponent in it, but 3 is just a constant, and the easiest constant to use is going to be a 1. So 1 over 5 to the n, that would be a good AN to choose, and then we know that this is a geometric series, so that makes it, well, it's a test that we already know. Here's another example. If Bn is 1 over 3 to the n plus n, well, I have another variable down here, but 3 to the n is so much bigger than n, because we have like 3 raised to the infinity. You can think about it, like, if you have trouble figuring out which one's bigger, think about if n is infinity. So 3 to the infinity is so much bigger than infinity that we can just ignore that plus n, and then we get 3n here, and then the 1 on top can just stay a 1. So this would be a simplified version of this. Basically, we just want to get rid of the extra stuff that we have. And this doesn't always work, but it's just a tip to give you something to try if you're going to use the direct comparison test. The second tip is to choose something that you know the convergence of, or you can easily find the convergence of it. So for like this one, I have 3 over n factorial, which is, I don't have a test for n factorial specifically, but it kind of looks like I have an n on the bottom, I have a constant on the top, so why don't I just do 1 over n, and I know that's the harmonic series, or you can think about p series. But this one diverges because that's an easy one to find, whereas 3 over n factorial is not easy to figure out the divergence of, or the convergence of. Here's another example. So I have 1 over this trinomial down here, and I don't have a good test to use for a trinomial, like not up till now. It's not a geometric series, it's not p series or something. But if I ignore all of the smaller terms, I look like I have 1 over n to the 4th, which is p series, and I know the p-series test, so 4 is greater than 1, which means that this is going to converge. But it's really easy to figure out since it's a p-series. Alright, another tip is, the first thing you want to do, you have to make a conjecture about whether the series that you're given in the problem, make a conjecture about whether it converges or diverges, because that'll help you maybe figure out a series to pick for AN. So here's an example. If I have this series that I'm given in the problem, 1 over n to the n, that one, I can't look at it and figure out I can't just do a p-series test or a geometric series on it. But I know that infinity to the infinity, or like 100 to the 100, whatever, this denominator gets really big really fast. So that means that this series is probably converging, because this fraction is going to go 1 over something huge is getting close to 0. So I'm thinking that this probably converges, which means, okay, this kind of looks like 1 over n, which I could use, but 1 over n diverges, so I probably don't want to use that since I'm looking for something that converges. I could use 1 over, and since I can't ignore the exponent n, maybe I keep the n in the exponent, and then I change this n to a constant, and it doesn't matter, I just picked 4 because I wanted to write a 4. So if I pick 1 over 4 to the n, that converges, so we could probably use that. Another option is that maybe instead of getting rid of the exponent and well, we didn't get rid of it, it's a 1, but maybe since we need something that converges, we can pick an exponent that would make it converge. So we could maybe use 1 over n to the 4th. And we'll see later on how we can test these series to see if they will work. And it could be that you try one and it doesn't work, and so then you have to come up with something else. There's not just one right way to do or there's not one right series to compare. There's lots of different choices that you could make for an. So if you and the person beside you choose a different an, that's fine. Alright, so here are the general steps for the direct comparison test. The very first thing you want to do is make a conjecture about whether your series converges or diverges. Sometimes that's hard to figure out, though, and so sometimes step 2 is a little bit easier to do first. If you know if your series converges or diverges, if you have a conjecture about it, then if you think it converges, pick a series that converges and looks like your series. If you think it diverges, then pick a series that diverges and looks like your given series. And if you couldn't make a conjecture, like if you just looked at it and had no idea, then maybe pick something that looks like your series and see whether that thing that looks like it converges or diverges. And then after you have picked your series, the next thing you need to do is compare the two series, the one that you were given in the problem and the one that you just chose in step 2, the an. If your conjecture is that it converges, you want the one that was in the problem, to be less than the one that you chose, because it needs to be smaller than a converging series. If you think that it might diverge, then the series that you picked should be smaller than the one that you're given, because you want your given problem to be bigger than a diverging series. So that was a lot of words. Now we're going to do an example to see what exactly this thing looks like. So the problem tells us to use the direct comparison test to determine if the series converge. There's going to be 2 parts, so there's an A on this slide, and then we'll look at another example on the next slide. But our first series, we have 1 over n squared plus 1. Okay. This is the given one, so I need to figure out what I'm going to choose, or you can think about this. This is your bn, and we have to find an. So my conjecture for this one, as my n gets bigger, as I get closer to infinity, this denominator gets bigger, so I'm going to think that I have like 1 over something huge, which is kind of 0. So my conjecture is this converges because these fractions get smaller and smaller and smaller. I could be wrong. That's why we call it a conjecture instead of, like, yes, it converges. It's just a conjecture right now. We're testing it. Okay, so my bn was 1 over n squared plus 1. And if I simplify that, if I just ignore that plus 1, it kind of looks like 1 over n squared. So I'm going to choose that for my an. And then the nice thing about this being 1 over n squared being an is that this is just a p-series, and p is equal to 2, which is bigger than 1, so that means that this series, an, does converge. Alright, so I've got something that converges. I want to prove that mine converges. So my given problem here, needs to be smaller than the converging series over here. So I make that an inequality. Bn is less than or equal to an, because it's converging. If it was diverging, we would switch this to be greater than or equal to. Alright, so I need to prove that this statement is true. You can do that however you want to. You can do it algebraically. You can look at a table of values or a graph. This one's easy enough algebraically, so I'm just going to do that. I cross multiply, so I get n squared is less than or equal to n squared plus 1, which is true because we can cancel out the n squareds maybe, and then we get 0 is less than or equal to 1. And because that's a true statement, that means that our original series converges, just like we thought. But now we know for sure. Yes, it converges. Alright, so the second part, I have the series natural log of 2 over n plus 2. Looking at that, I have no idea if it converges or diverges. I know I have a conjecture written down for this, that it diverges, but this is how I got my conjecture. I actually went ahead to step 2, and I said, alright, I have natural log of n over n plus 2. And I haven't done like p-series or geometric series with a natural log, so I'm just going to ignore that and change it to 1. And n plus 2, I don't really need the plus 2 because it's a plus a constant, it doesn't really matter. So I'll take the n and I'll put it over here. So natural log of n over n plus 2 kind of looks like 1 over n. And I know that 1 over n is the harmonic series, so it diverges, or more formally, you can say that it's a p-series where p is equal to 1, which is less than or equal to 1, because that was what we need to know for the p-series test, so this diverges. So then I can go back in and say my conjecture is that it diverges. But it's important that at some point you explicitly state to yourself, okay, I'm trying to prove that it's diverging, or I'm trying to prove that it's converging, because that tells you what to do with your inequality. So my conjecture was that this diverges. So I need the chosen series, my diverging series that I know for sure, should be less than or equal to the one that I'm trying to prove. And then I need to simplify this somehow. So let's multiply n plus 2 over on this side. So n plus 2 over n is less than or equal to natural log of n. And then this needs to be true for really big values of n. So like as I'm going towards infinity, n plus 2 over n is really, like the plus 2 is not important, so really I just have n over n, which is the same thing as 1. Natural log of n, as I go towards infinity, it goes towards infinity, so I end up with 1 is less than or equal to infinity, which is true, so this series diverges. Another way to do this would be to look at the graph of these two series and see which one's bigger as you keep zooming out, and this one is going to be larger than 1 over n. So that means that that this inequality is true and the series diverges. Here's one for you to try. So use the direct comparison test and determine if the series n plus 2 over n squared converges or diverges. Pause the video and we'll talk about the solution when you come back. Here's another one where the conjecture was a little bit hard to pick, maybe. It could go either way. So what I did first, I just put a little question mark here because maybe I don't feel like making a conjecture until I see what it looks like. So n plus 2 could be the same as n, basically, or not the same as, but similar to n. And then n squared looks like n squared. So now I have n over n squared, which kind of looks like 1 over n. And by the p-series test, I know that this diverges because p is equal to 1, which is less than or equal to 1. The other way I know that this diverges is that it's the harmonic series, and I know that about the harmonic series. Alright, so now I have this word diverge, which means that my chosen series, I know this diverges, so I need to make sure the one that I have is bigger than a diverging series. So I set up the one that I've chosen is less than or equal to the one that I'm given, and then I try to solve this. So I'm going to bring the n squared over to the other side, because now I can simplify this and get n. And on this side I have n plus 2, n plus 2. So n is less than or equal to n plus 2, which means whatever number I have, it's less than or equal to that same number plus 2, which is true. You can also go one step farther and cancel out the n, so you have 0 is less than or equal to 2, which is true. But because that's true, and we had a diverging series that was less than our series, that means that n plus 2 over n squared diverges. And that is the end of the video. We're going to learn a couple more tests, but we are almost done with all of the divergence tests now.